Okay, welcome to the stream. Let us get going. So yesterday, was it yesterday? Yesterday we were having an issue with our system working. So I found two issues. The two main issues there was an error in the HLS code where we were using the blue color instead of the red color, and so that kind of broke things. And I'll show you where that was. And the other thing, we had to restart our SDK. Our SDK board support package was based upon a different system, and it just wasn't working correctly. So I needed to delete the SDK, restart it, save the important files. But let's go. Okay. Oh, so let's first get the resolution available so you can see a little bit better. So we're gonna go 150 over there so you guys can see. Let's minimize my taskbar. Okay. And then we'll throw up HLS, and it's gonna be so happy we did this. Okay, so let's talk about our first error. So if we go to the source code, okay, this section right here had blue instead of red, and that caused an issue. So we fixed that, redid the SDK, and we're good to go. So I just ran it. We're going to cd into c/Xilinx stream image proc. Then we're gonna do targets. Targeting the correct one. We're going to do down data test _00 bin. We're going to do that into the DDR. Frame buffer is that's going. So let's switch my screen over to HDMI so we can see what's happening here. I also need a tera term. Tera term. I'm gonna go COM10. Didn't like that. So let's go to that terminal receive auto. So let's see. The software now. There we go. Okay. Back to our screen. Okay, cool. Pull up webcam. So we're gonna give you a picture of the beautiful blue screen about there. And now we're gonna load our image again. So let's load our test image. And it's slowly loading in. So what we've done now is that we can do our filters on each channel. I'll go ahead and show you the channels individually, and I'll show you what we can do to combine the channels to maybe get more additional information. We still have the option to grayscale it if we want to grayscale the image. So, okay, the image is loaded. Let's turn off the channel. So we have the blue channel. So press 0 to blank the channel. Go to green channel, blank the green channel, so we have red. Now we can go to blank the red channel, turn on the green, turn on the blue. Now we have all the channels. Now if we turn all the channels off and just go to blue, identity, outline, sharpen, emboss, bottom subel, left subel, top subel, right subel, and blur. And we can do this for each channel. Now the image is blurred completely. Now we can do some interesting things. We can do like a bottom and top. So let's turn off red, and blue will be a bottom, and green will be a top. Or better yet, be a left or right. Left or right doesn't really seem to change that. I think it would change it more dramatically if it was if it was bigger kernel. Since it's such a small kernel, it's grabbing all the lines very easily. And then we can maybe introduce a red emboss. We can get some like cool color effects, or we can have stuff like this. So let's load in test image 1. I like fun one to play around with. So do red embossing and red embossing. Effects, sharpen blue, emboss the blue, outline. Maybe if we take the green and did so we have all the channels, and then we can grayscale the image on the outside. The output grayscale only works if they're all the same. We get some cool colors like that, or we can turn off grayscale. Rocket has color. Grayscale it. Okay, so we have it working. We have the code. We got real-time video editing on image processing, 1080p at 30 frames per second. What can we do to change it? I think we have enough fabric to do a 5x5. So let's sit down real quick and try to do a 5x5. So let's go to HLS, and we're going to try to do a by 5 kernel. Try to do by 5, and it's going to be a 25. We're not doing that right there, so that's the issue. 25, oh, 25. Okay. So we're not even using the Y operation, so we can remove that guy. That's not even happening, so that. Okay, so four, 3, 5, 6, 7, 8. No. Window. Open declaration. We're gonna make it a 5x5 window. Maybe I'm gonna take this real quick. Control A. Save that into a new document. Sure. We're gonna call this C3. Okay. Sure. So we're gonna go back to the HLS. Control Y. Then 11, 13, 1, 12, 22, 13, 18, 23, 19, 19, that's going to be 14, be 24. Okay, 5. Okay, so that's good, that's good. It's all the change we need to do there. 5 there, that's good, we don't need to do that. Buffs are the same. We're going to do a mod 5. And what we're going to do is we're going to backtrack on that one. So now what's going to happen is when we're doing 0, 0 is at the bottom, it's going to go 0, 4, 3. And it's going to be 4, 4, 4, 4, 4, 4, 3, 2, 1. And 3, 4, 3. I think it'd be better if we just then have to get the software to support this larger filter size. It's gonna be interesting. I would try to parameterize this a little better with a for loop, but we saw that they used a lot more LUTs. That wasn't very convenient. Okay. So it's gonna be 1's here, and it's gonna be 0, 4, 3, 2. 0, 4, 3, 0, 4. So we're gonna do 2, 3, and 4. 2, 2. And so we're gonna go 1, 0, 4, 3. 1, 0, 4, 3. 1, 0, 4. We're gonna do 3 here, 3 here. So we want to place that with a 1. Okay, we have a 3, so that means we're gonna go 2, 1, 0, 4. 2, 1, 0, 4. Check. Okay. So it's gonna be 2, 1, 0, 4. 3 is new row. And finally, we have 4. 4 is being loaded in. 4 is replaced by 1. 1. This is basically going to go 3, 2, 1, 0. 3, 2, 1, 0. 3, 2, 1, 0. Okay, that should work fine. That all should work fine. RGB, 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 RGB. 1, 2, 3, 4, 0. Where's it the same? 4, 2. G G G B R 3 1 4 3 0 4 3 0 B's G's R's 4 4 4 there 4 3 2 0 3 2 0 G's G's R's. Okay, looks good. Let us try to synthesize it and see what we get for our 5x5 kernel. So before we had a 50%, well, it guessed a ridiculous utilization, like 20,000. So let's see what this gets for us for utilization. So we got what we want utilization wise. It says we're using basically the entire chip. How are we doing on VRAMs? We're using 15 now. Let's see. How much do we have free on our design? VRAMs. Okay, VRAMs 56. We have a total. Okay, we should have 15 free, so we should be good. Let's see if we can get this 5x5 kernel filter, and then I'll go read up on how we can do a 5x5 Sobel filter, a 5x5 other kernel filters, and we can try to fill in the software with that. Then we'll have to update the software. Export the RTL. I want to see what we have in our driver software. Probably should make a new SDK. Yeah, it takes a whole lot of time. That should probably make a macro for getting these kernels and just timesing it by 8 or something. Oh, yeah. Okay, so that's good. It's good. Now let's throw it into the deep end. Open block diagram. We're going to refresh it, build it, and upgrade this. Generate it. See what the generate is. So it was estimated to have. Come on. It was estimated to take up 39,000. We're going to see when we generate it what it's going to be. Go down. Okay. Let's go ahead, background that, okay that, we can look at the design runs. Like it's finishing it right now. See how much it takes. Okay, it's still running. I guess go look at the log as it finishes up. So we just created a 5x5 kernel filter. I don't even know if it's going to fit in the FPGA. I guess I could try to simplify some other things to make it work, but I don't know. We might be able to, I would maybe decrease the frame buffer in the VDMA. It would give us a little bit of fabric and a little bit of VRAMs. I could, now that's about it. The clock is already pretty slow, so it should be fine. Yeah, I think we're gonna be out of luck unless we somehow remove the microblaze or simplify the microblaze a bit. Okay, getting close. Yeah, we should probably add a function where you can like load an array in, pick the filter, pick the array, and then just create a function that automatically assigns those values. Yeah, we could probably do that. It'd probably be the easiest way to not go crazy and copy and paste everything. Okay, this finished. Let's see, flip flops 28,000. I hope we can fit it. Increase the BRAMs by half. Okay, cool. Looks like we're done. So yeah, let's go big or go home. So it's going to do synthesis, implementation, try to squeeze this on the FPGA. We may not have enough resources. This is going to be tight. Okay. So I guess in software, let's try writing some for this. We can try to mobile 5 kernel. Cool. I was expecting that real easily. Okay. Outline. Great how Google works. So this one. Simple box blur, Gaussian blur, line detection, edge operator, Gaussian operator, Gaussian of Gaussian. Try that one. So I assume we just do that on a greater scale. Gaussian blur. Shift those values over. Yeah, we can play around with trying to do a little bit more complicated one. That's a fun one. Edge. Blur, emboss, outline, sharpen, fill. Okay, so I think we should be able to do it. Okay, so auto running place. If it gets past place, we should be good. Oh no! We have oh about 2,000 more than what we can do. Let's go to implementation settings. Let's see. Op design, directive, floor. Explore. Let's try that. Okay. Rerun implementation, set and read. Okay. So go back to the block diagram and see if we can squeeze in a little bit more fabric, right? We should be good there. That one. And I should pull up the thing and see what. We're gonna have to go open synthesize design, and then I'm gonna pull down the hierarchy of the utilization, and we're gonna try to fit this in to this FPGA. So I said we need about what 2,000 LUTs. Figure out how we can squeeze 2,000 LUTs. So it's about 5% of the FPGA we need to free up. Okay. So let's do reports station go. Let's figure out if we can find a place for 2,000 flip-flop. So the Axie memory interconnect. Good place to look. MIG. Later. So I see the MIG and the Axie memory. We can decrease the VDMA a little bit. Use a little room out of that. Filter operator. That's what we're looking on. Yeah, I mean we can go microplay settings to make it stupid as possible. I think that's gonna be about it. So what's our Axie memory connect on? We're on custom. Let's try minimize area. Last time this didn't work, but we'll go find out anyway. Oh, we can't do this while that's running. That's fine. Nothing we can do about the MIG. All these Axie. Some of these not naming like this guy doesn't need to have an Axie port. Maybe we just take his Axie port away. I kind of like that idea. We're gonna take his Axie port away. Evac stream is required. That's good. MIG. Nothing we can do to edit that. Clock wizard got clock wizard is required. How much does the local memory take up? I bet the port on it's causing more contention than it needs to. We're gonna look at local memory. Yeah, local nothing. Microplays. Okay, we got. Did we get any better? Okie dokie. So what we're gonna do? I'm gonna make you minimal area. Hopefully you work. May not work. Let's go into the microblaze settings. Select area. I think we should get there. Do they have cache? No, we don't have any cache. We're good. Do magical VDMA, buffers. Okay, with line buffer. Drop that to 512. Keep that. Press width, frame buffer. I think that's about it that we're gonna get from that guy. Pixel unpack. 5. Press edit. Press. Okay, we've removed pixel unpack, so let's exclude segment. Unmaps. Okay. Now, can we test validation? I know the axis is not connected. Just gonna deal with it, okay? Okay, cool. Validated. Save. Try to run synthesis, shall we? Will we be able to do it? I'm not sure we'll be able to do it. Well, once it passed synthesis, we might call that a day and look at doing the software tomorrow. But yeah, we're getting to the physical limitations of our chip. I mean, our other solution, so we have another solution, is we can try to implement the 5x5 kernel in HDL. And that could probably be significantly smaller. And yeah, significantly smaller IP, and then we could probably try to increase it as much as possible, which would be really cool. Yeah, we could have some really fun stuff with it. Yeah, we could definitely do that. It'd be fun. Yeah, so we'll probably, if we can't get the HLS synthesis to show better, if it pass synthesis, we'll do implementation, and then we might call it good. Well, any other questions from our loyal viewers? I guess we could move to a different board. We could move to the pink, and the pink would has a much better platform for this. We could do 1080p, 60 frames per second. We'll have plenty of more LUTs go around. PDRs on the ASIC part, and we have a processor. It would just overall be easier on the pink. I guess I was just trying to do the Arty board to start off with. We don't really have can't really do a good VDMA on the icebreaker. It doesn't have the DDR necessary to do that. We got some boards coming in about latest chips that we might be able to do it on. Okay. Watch this go. Oh, still got some time to go. Okay. Well, we'll have to maybe shut down early, and then I'll go over the results of this on the next stream tomorrow. And we can see our progress in trying to get this to fit on a small FPGA. We call it small it's a good size. It's 200K LUTs, right? So it's a very large FPGA. A lot of the IP Xilinx uses is, I would say, bloated, feature rich, whatever, which other word you want to use. So it's probably slowing us down a little bit. If we did this all in custom HDL, we'd probably be so good. So we wouldn't be able to use HLS. And I feel like a feature here is we're exploring the tools of HLS here. How can we use HLS to make the tools we need? Not running or something. Feel like just stuck. Okay. Well, it's coming to 8:30. I will keep an eye on this. If it gets stuck, I may have to reset it. Vivado gets stuck sometimes. Okay, I think that's probably the best place to call it for tonight. I'll keep an eye on this. Have I guess we could. We've already kind of showed our pictures before. That and showed the settings of the colors. I think that's about it. I think there's much more we can show you. Initialize. Okay. So running synthesis on this. Synthesis finished. That's good. Yeah. Okay, yeah, I'm not gonna make you guys watch logs. I'll keep an eye on it. So thanks for watching today. I guess I'll see you guys tomorrow. Bye.